locomotion of fish, and what it means to move, and what it means to move in the ocean, in water, and what that means in terms of the physiology. And I pointed out that there were some fish that are what we would call high performance. They're very, very highly adapted to moving through the water. They can move through the water like nobody else can, very efficiently, very fast, and it gives them a huge edge over other fish and over their prey and predators that are trying to catch them. And so they're exquisitely adapted to the marine environment in terms of movement, locomotion. So that's what we're going to talk about today. First of all, what exactly do I mean by high performance fish? I said some of this. They can swim very fast. This includes the fastest fish in the ocean. They're very good predators. And what that means is they can exploit niches that aren't available to other species, whether that's fish. Some of their main competitors are marine mammals, which have a high metabolic rate, warm-blooded, warm-blooded, and so it's along those lines. But they can even swim faster than marine mammals. And they've got a number of adaptations that we're going to go through that make them not only very fast, but very efficient moving through the water. And I think a very good way to illustrate the difference between a high performance fish and just a regular fish is with something I'm very familiar with, a couple of species of shark. And we can look at blue sharks, which is an average shark, and a mako shark, which is a high performance fish, one of the most high performance fishes out there. So we're going to compare these two, and we're going to look at morphological features that you might think, well, that's morphology, that's not physiology. But again, we concentrated on this to a certain degree in the first lecture, that morphology has a big influence on physiology in terms of energy, energy efficiency, energy use. And so it's worth talking about morphological features because they directly influence the physiology of these two different species of shark. Then there's some specifically physiological differences in terms of their circulatory system, in terms of blood and muscle. And so we'll look at those as well as their gills. It's basically things that allow them to maintain these high levels of activity and move efficiently through the water compared to an average fish or an average shark. And then there's also some biochemical differences. And ultimately, what this translates to is a different ecological roles for a high-performance fish versus an average fish. Okay, well, you probably remember, I'll let you watch this. Well, the point is, you probably remember this Aesop's fable of the race between the tortoise and the hare, and the point being that the tortoise is an average thing. It's not just average; it's very slow, and the hare is very fast, and it's got a number of adaptations that make it very fast. And so if you had a race between those, if you had a regular race, then of course the hare is a big favorite, and the hare is going to win. And Aesop's fable, it's a different outcome, but we'll talk about that in a minute. But basically, comparing these two sharks, you've got a blue shark that's an average shark. It's an ectotherm, cold-blooded. It's a generalist feeder, compared to a mako shark, which is one of the fastest, if not the fastest, fish in the ocean. The regional endotherms. We looked at that characteristic heating parts of the body part of the time in the thermoregulation unit that we covered. And they are a very specialist feeder. Basically, whatever they want to eat, they can get, they can catch, and they can eat. So these are two very different sharks. And so the idea is you've got a hare in terms of a mako shark, and you've got a tortoise in terms of a blue shark. You find these together, the same place, swimming right next to each other sometimes. So you might think, it's a race between the tortoise and the hare. They're on the same racetrack basically because they're in the same water. Sometimes you can even see them swimming next to each other from the same boat. Okay, well, in terms of differences between these, we'll look at morphological differences, which, as I mentioned, you might think morphology, that's not physiology, but we'll see how that translates to physiology. And then these different systems, physiological systems, the circulatory system, the muscle, enzymes, how that works, and then the delivery of oxygen, which is important for metabolism, and then some biochemical differences, and ultimately how it all translates into the ecology of a high-performance fish versus an average fish. In terms of the morphology of a blue shark versus mako shark, there's some major differences between the two. If you look at the whole body of a mako shark, it's a much more fusiform shape than a blue shark. A blue shark's longer and skinnier and fat and flatter, but a mako shark has this tuniform shape, this shape like a tuna. It's this torpedo shape. It's this fusiform shape that we looked at in the last section and saw that if you take a sphere and move it through the water, then there's drag that's created. There's this turbulence that's created behind the shape that creates more drag and interferes with the efficiency of moving a sphere through the water. If you have a fusiform shape, then this is the flow of the water, and this is the direction of the drag. There's far less drag, much more efficient moving through the water, and what that means is less energy per unit distance moved. So fish that have this shape, turtles that have this shape, penguins that have this shape, mammals that have this shape, very efficient moving through the water and can move a certain distance with a minimum expenditure of energy. That's the mako shark. If you look at the blue shark, they've got their body is somewhat fusiform, but not nearly as much as the mako shark. They're a lot longer and skinnier. It's like a fusiform shape that's, you take both ends and stretch it out. So a lot less efficient moving through the water, a lot more drag that's created by the blue shark body moving through the water than a mako shark. If we start at the head and look at the head, the mako shark's got a very cone-shaped head and that tapers back to its fusiform body, so a minimum of drag that's created by this head and a maximum of efficiency moving through the water. If you look at the head of a blue shark, it's a lot longer and flatter, and it's not all about moving through the water with a minimum drag. Part of the properties of the flat head of a blue shark is that it generates lift, hydrodynamic lift. So it's not about reducing drag necessarily as it is about providing lift. So very different heads and contribute differently to the amount of drag and contribute differently to how efficiently you can move through the water, whether you're a mako shark or a blue shark. If you look at the fins, these blue sharks, again, have big lifting surfaces like their head. They have these long, skinny pectoral fins that provide a lot of lift, but they also provide a certain amount of drag moving through the water. If you look at mako sharks, the common name for these mako sharks is short fin mako sharks, and they do have short fins. And so the fins serve their purpose, some lift and some stability for the body so that it doesn't roll around. But there's a lot less drag with a small fin compared to the big fin of blue sharks. If you go all the way back to the tail and look at the tail of a blue shark versus a mako shark, then the blue shark's got the typical heterocircle tail of a shark, with a big upper lobe and a lower lobe that's a lot smaller, and as this tail moves back and forth, it creates forward propulsion, but there's also a lot of drag that's involved in a tail like this. If you look at the tail of a mako shark, it's lunate, it's quarter moon shaped, which is very efficient for moving back and forth through the water, also providing a lot of forward propulsion. So the tail is almost homocircle, not so heterocircle. The upper and lower lobe are almost the same size. Very different tails, very different response to the environment moving through the water in terms of drag that's created and in terms of power for forward propulsion. And if you look right in front of the tail of mako sharks, see these very prominent keels. And we saw this in the other lecture. If you have keels and structures like that just in front of the tail, when the tail moves back and forth, there's turbulence created right in this area. And what follows right after this is the tail. So the tail is beating back and forth, not in regular water, but in water that's been all chopped up by this keel, turbulent water, which makes the tail beat back and forth more efficiently with more power and less drag. So if you look at the whole body of a blue shark versus a mako shark, blue shark swims like an eel. In fact, it's got this anguilliform, which is another name for an eel, swimming. It bends its body quite a bit, and these yellow areas show where there's drag from water hitting against the body of these sharks. If you look at a mako shark, then the only part of their body that bends and that's facing this water head on is the very last part of their body. In fact, if you look at how much of the body bends in a mako shark, here's a mako shark or a tuna, and you see that it's all the way down here. Most of the body stays pretty straight except for about the last third of their body. So it's only about 30% of the body that bends compared to, look at this blue shark, it's almost the whole body that's creating drag. Whereas for these very fast swimmers, they're just basically the very end of their body is moving back and forth. It's a very powerful propulsion that's generated, but it's a minimum drag. A lot of power, a little drag, and that's what you see for mako sharks. You definitely don't see that for blue sharks or your ordinary shark. And so, in terms of the story of in terms of the story of the tortoise and the hare, most of you probably know the story that the hare takes a nap, gets so far ahead, complacent, and then the tortoise is going along steady, slow and steady, and trying all the time, and the tortoise wins because the hare wakes up too late. And so here's what happens. So it is a fable. It's a fable. It's not real. It's complete fiction. And if you had a mako shark representing a hare, and if you had a blue shark representing a tortoise, there's no way that tortoise would ever beat the hare. So there's some similarities, but again, it's a complete work of fiction. And the hare is going to win because it's got so much of an advantage over the tortoise. And so let's look at some of those things. In terms of physiology, we looked at the morphology and saw how there's, you can compare blue sharks and mako sharks, but to a certain degree, there's no comparison. That these mako sharks are much more efficient at moving through the water. They can move faster with less energy per unit distance. In terms of their physiology, which is what this class is about, we saw that if you look at the circulatory system of a mako shark or other regional endotherms, they have these rhesia. They've got rhesia that heat certain parts of the body. And if you look at a mako shark, they've got orbital rhesia that heat their eyes. They've got visceral rhesia that heat organs inside of them. And then they've got this lateral rhesia that heats certain parts of their body, particularly the muscle. And if you look at the distribution of muscle in the body of these mako sharks, then you see that, remember, there's a difference between red muscle and white muscle. And in sustained swimmers that are swimming all the time and very fast and very powerfully, there's a lot of red muscle. So if you looked at this mako shark, this is the skin of the shark, and if you went from the skin towards the anterior, you'd see parts of this have this circulatory system with the heat exchangers where it's red muscle that's heated. And so part of their body, especially this part of right around the middle of their body and the core of the body, has an elevated temperature. We'll see that's where there's a lot of red muscle. So it's red muscle in addition to their eyes and in addition to these organs and all parts of the body, but it's specifically this red muscle that's being heated. So if you took the temperature of a mako shark, for instance, at different locations, then here's the outside of a mako shark, here's the other side of the mako shark. This is a mako shark that's cut in half and you're looking head on. And what you see, the distribution of this red muscle is right here. This is the vertebrae. This is the body cavity. And so right on either side of the vertebrae, deep in the core of the body of this mako shark is a lot of red muscle. And that red muscle is right smack in the center of the area of the body that's being heated. So if you look at the body temperature of a mako shark, here's a shark and you're sticking a temperature probe in here at different locations, then what you see is this is in water that's 10 degrees. As you get farther and farther into the core of the body, right around where this red muscle is, that the temperature of that muscle might be 14 or 15 degrees above the ambient water temperature. That results from the circulation, is risha, that you find in mako sharks, and of course you don't find anything like that in blue sharks. And so if you look at different organs, or if you look at that muscle itself, and if you look at the body temperature of a shark that's swimming around in 10-degree water, then these are some measurements you might find in a mako shark. Here's our mako shark. It could be 4 degrees, 6 degrees, 8 degrees, 10 degrees, even 15 degrees warmer than the ambient temperature. This is just from one study. When it was elevated, the liver and the stomach and the intestines and the brain and the eyes are all warmer than the ambient temperature. And you've got some of the cousins of mako sharks in some of these studies that were elevated even more. 8 degrees, 10 degrees, 13 degrees, 14 degrees above the ambient water temperature. If you look at a typical shark like a blue shark, then it would be like this basking shark where their muscle might be 1 degree warmer just from metabolic heat, but it's pretty much going to be the same. So mako sharks, they can heat all different parts of the body, but especially that red muscle. So we'll look at that more in a minute. So this idea of heating your body and having this special circulatory system with those risha, those heat exchangers scattered around in different parts of your body, your eyes and your viscera, and especially that muscle, the red muscle, then it costs a lot in terms of energy. You have to generate heat metabolically. That means burn fuel, which means you have to eat more, you have to have more water and things like that. So it's energetically costly. So what do you get out of being warm-blooded? What are the benefits? We're going to concentrate on a few things, especially the muscle. But here's some things that can happen with if you heat your body. Tail beat is faster. If you can beat your tail back and forth, it's generated by muscle, and muscle is contracting more efficiently, as we'll look at in a minute. If you can beat your tail back and forth, you can swim faster. Makes you a better predator. Makes you able to be the super predator, escape from all kinds of predators that are trying to eat you. If you can heat your muscles, then you have a lot more stamina, which means that you can chase after things longer. You can cruise a lot farther. You can be active and maintain high sustained swimming for a long time. Your stomach temperature and digestive system temperature is higher, which means you can digest food faster and pass it through your digestive system and be ready to eat more. This is energetically costly, which means you have to feed yourself more. You have to stoke the fires more with more food. And then if you've got these brain and eye heaters, you can process sensory information faster. You can make decisions faster. It adds to your super predator capabilities. So we looked at some of that with when we were looking at thermal regulation, the advantages. And then there's some speculation about if you heat your reproductive system, maybe your gestation period is slower, you can reproduce faster. The jury's still out about that. But ultimately, you can increase the habitat that you can occupy. You can go into very cold water. You can go into deep water, which is cold. You can go into high latitude water, which is cold. And you're warm-blooded there, almost, part of you. You're moving around fast, where everything else is slow, except for other warm-blooded animals like mammals or birds. So it's a fantastic advantage that you have if you can heat your body for all these different things. Makes you a super predator, basically. Okay, well, let's look specifically at muscle, what this muscle does, because we saw, or I pointed out a number of times now, that if you're a sustained swimmer, if you're a super shark, super predator, tuna, something like that, you're going to have a lot of red muscle and not as much white muscle. If you're a ambush predator or you're a prolonged swimmer, you swim for a while and then you have to rest, you're going to have a lot more white muscle. And in fact, if you look at red muscle versus white muscle in mako sharks versus blue sharks, then we'll see that there's red muscle in blue sharks, but the red muscle in mako sharks is more concentrated. There's more of it, and it's all concentrated around this one location in the core of the body. And you know what the characteristic of that area is? It's warm. So it's warm red muscle. It's not just red muscle, but it's warm red muscle. And so we saw that the red muscle, the way that it twitches and the amount of mitochondria and ATP, it can sustain contraction. It can contract and contract and contract and contract, and it doesn't fatigue, and it doesn't get into oxygen debt, whereas white muscle does. So if you look at where you find red muscle versus white muscle on a blue shark, they're very different locations. But let's look for a minute about these characteristics of red muscle. What makes red muscle so special if you have red muscle? So here's a cross-section of the muscle of a high-performance fish, and it shows this red muscle that's got a lot of enzymes and it's got a lot of ATP producing capabilities. But this red muscle is slow twitch, so it's capable again of contracting and contracting and contracting and contracting. And there's this myosin, one of the protein filaments that is in muscle that slides past another one. When muscles contract, they contract at different speeds. And the white muscle, for sprinters, you have white muscle that contracts quickly, but you go into anaerobic debt quickly. You use the oxygen, use the energy, and then you're spent. You're sprinted 100 meters, and then you're done. You can't keep racing. If you look in red muscle, it's got that form of myosin ATP. It's a slow form. It's an enzyme that generates ATPase that works relatively slowly, so that the muscle contraction is relatively slow. If you look at the concentrations of these things in red muscle versus white muscle, there's a lot more myoglobin. Again, you remember myoglobin from respiratory physiology. Stores oxygen. It has a high binding capacity for oxygen. A lot of mitochondria. Hopefully you remember from some biology class that mitochondria is the site of ATP synthesis, the energy powerhouse of the cell. It's got a lot more enzymes that are related to basically making ATP and burning fuel. It's got a lot more lipid in red muscle, source of energy, calories. And then in terms of the blood supply, there's a lot more capillaries that go to and supply red muscle compared to white muscle. So all of those characteristics translate into red muscle being sustained contraction, not running out of oxygen, not running out of energy, making a lot of ATP, and being able to work at a very high level, contract all the time, and not get tired. And here's what I was talking about before. If you look at a cross section of a mako shark up here on the top and a blue shark, if you cut this shark in half right along this dashed line, if you cut this blue shark in half and you look at its muscle, here's the vertebrae, and here's the bottom of that shark, and here's the dorsal part of that shark. This is just one half. There's all this muscle, very muscular, but most of that is white muscle. There is red muscle there. This is the amount of red muscle along the body of a blue shark, but it's spread out quite a bit from almost all the way to the head to almost all the way to the tail. If you look at the concentration of red muscle in mako sharks, then there's not very much up here. There's a big peak right along this dashed line, and then it tails off again. So if you cut a mako shark along this dashed line and you looked at that body cross section head on, this is what you'd see, all of this red muscle right here. And it's not just anywhere, but it's in the middle of the shark. And it's not just anywhere in the body, but it's towards the core, very close to the vertebral centra of the vertebrae, which is the warmest part of that shark. So there's a lot of red muscle concentrated there, and that red muscle is warm. And so what you find is that this red muscle is heated. This red muscle is at the core. This red muscle has this type of configuration, and it's basically like a piston of this really powerful muscle that's contracting very efficiently and very powerfully both. And this muscle goes back and attaches here in the back to the tail, pulls the tail back and forth, back and forth, back and forth, and it's doing that with this piston-like muscular arrangement, which is a lot of power. And it's not just any muscle that's pulling the tail back and forth, but it's red muscle with all those characteristics that enable it to keep going, and generate a lot of power. Well, if we look at the enzymes that you find in a high-performance fish versus a low-performance fish, we can see what's going on in blue sharks versus mako sharks. So here's a couple of enzymes. Here's these cardiac enzymes that are related to the heart beating, the muscle in a heart contracting. And if you look at the concentration of those enzymes, this cardiac muscle that's related to metabolic rate, how high of a metabolic rate you can maintain, then look at the difference between a blue shark and a mako shark. The enzyme activity in a blue shark is it's low compared to a mako shark. If you look at these two different enzymes, there's LDH, which is related to the ability to recover from fatigue and anaerobic respiration. Blue sharks don't have much of that capability. They're going to get tired. They're going to run out of oxygen. They're going to suffer lower pH in the muscles and those things, whereas a mako shark's got really high level. If you look at this citric synthase that is related to ATP production, look how high it is in mako sharks compared to blue sharks. So enzymatically, there's a big difference between high-performance sharks or fish, mako shark, salmon shark is another high-performance one. Thresher shark is related, but if you look at these more common, slow, average ectotherm sharks, then they don't have the same level of enzyme activity. And if you look at the effect of temperature on that enzyme activity in mako sharks, then you find if you heat your body, look what happens to the enzyme activity for citric synthase and LDH. They both go up. So you may be swimming around in water that's 10 degrees, but your body and where this muscle is likely to be 25 degrees. So look at the elevated enzyme activity in the mako shark if you can heat your body. It increases from about 20 to all the way up to 40 something. It more than doubles the level of enzyme activity. So it's not just that they have a lot of enzymes and those enzymes are very active, but those enzymes are sensitive to temperature. And if you can heat your body, those enzymes are going to work even faster. Well, something you need in order for cellular respiration is oxygen. And so, not surprisingly, if you look at the oxygen delivery systems between mako sharks, a high performance fish, and a blue shark, the average one, if you look at the surface area of the gills, that is 15 times higher in the mako shark than the blue shark. 15 times the surface area for oxygen absorption. We looked at this, some of those characteristics in our coverage of the respiratory system. If you look at the percent of red blood cells in the blood, red blood cells with hemoglobin, the high affinity for oxygen, reflects the ability of blood to carry oxygen. You've got a lot more red blood cells in the blood in a mako shark than a blue shark. A lot of oxygen, red blood cells. If you look at the capillary density, all the little blood vessels that are in the rhesia and that are in the gills and in the tissues, basically the site of gas exchange, it's a huge difference, 9 times higher in mako sharks than it is in blue sharks. If you look at the myoglobin concentration, that pigmented protein that's similar to hemoglobin in muscle, high affinity for oxygen and able to store oxygen in muscle, then it's 5 times higher in mako sharks than blue sharks. So all of this says, if you look at the difference between these two, the gills, the blood, the muscle of mako sharks, they're all geared towards delivering large amounts of oxygen to the mako shark. Circulatory systems are geared towards mako shark being fast and heating their muscle. The muscle physiology and the enzyme kinematics in the muscle are temperature sensitive and related to the red muscle. Fast, powerful movement of mako sharks compared to blue sharks. And finally, if you look at the lipids, then the most common lipid in the mako shark is triglyceride, which is the most common lipid you find in most animals. It's not that light, it's not that buoyant. Whereas blue sharks, they have more of this low density lipid, diacylglycerol ether. It's got a density of 0.89 compared to 0.92. That may not seem like very much, but that provides a lot more lift in the liver and the oil that's in the liver of blue sharks compared to mako sharks. Mako sharks, they don't need this hydrostatic lift. They have hydrodynamic lift. They're swimming, and not just swimming, but swimming very fast. Whereas a blue shark's lumbering along, it's generating lift from its head, it's generating lift from its fins, it's generating some lift from its heterocircle tail. And so this is the situation you have, is that if you look at the liver oil of blue sharks is a lot less dense than the liver oil of mako sharks. Blue sharks are relying on hydrostatic lift, which means they're being lifted whether they're moving or not. Whereas mako sharks, they don't need any of those kind of lipids because they're deriving so little lift from being light. They're generating lift from moving. And so what you have is the blue shark is kind of like a glider plane with these long wings and a small engine. Well, these don't have an engine, but if it did have an engine, it'd be a plane like this, moving along slowly and a lot of lift that's generated in light because they've got these low density lipids. This is a mako shark. Look at that, small wings, the tail is different. Everything about this plane and everything about this shark, fast. And so that's the difference between these two sharks. Now, towards the end of the story, what are these two sharks doing? Like I said, you're out on a boat, you see a mako shark, there's a blue shark. Blue shark, mako shark right next to each other. They occupy a lot of the same area, but you've got a super shark in the form of a mako shark. You've got a high performance shark, and you've got an ordinary shark. So what does that mean in terms of their ecology? Well, if you look at what blue sharks eat versus what mako sharks eat, then that will shed some light on what they're doing out there. But first of all, if you look at the metabolic rate of blue sharks versus mako shark. No one's ever measured the metabolic rate of a blue shark, but the odds are it wouldn't be particularly impressive. They would have a metabolic rate of a typical average slow shark that maybe would be somewhere down here. Whereas if you look at the metabolic rate of mako shark, it's faster than any other shark that's ever been measured. It's not just faster, but it's 2 times the metabolic rate of a lot of typical sharks. So mako sharks need a lot of energy to fuel their superpowers for being a high performance shark. It's not cheap. It takes a lot of energy for them to be a high performance shark. And so even though we don't know what the metabolic rate of blue sharks is, it's bound to be a fraction. It might be half, or it might even be a quarter or a fifth of the metabolic rate of a mako shark. What that means is mako sharks have to consume a lot of energy to fuel these superpowers. And if you look at the estimates of how much a blue shark eats versus a mako shark, again, blue sharks, no one's ever estimated daily ration in blue sharks, but the odds are they might eat about 1% of their body weight per day. They'd be more like a typical shark. There's other species of shark like the spiny dogfish and the lemon shark and the sandbar shark, and another study with the spiny dogfish and the lemon shark. These typical sharks eat maybe 1% of their body weight. One study with mako sharks estimated that they eat 3% the body weight per day, which is 3 times most sharks. So they have to eat a lot. But if you're the fastest thing out there, if nothing can outswim you, then that's not really that much of a problem. So what do you do if you're the fastest shark out there? What do you do if you're the fastest fish in the ocean? Well, you can eat whatever you want. And what mako sharks want is bluefish. Bluefish, bluefish, bluefish. Or there's a story I know that I'm sure you guys read this when you were younger, a few years ago. 1 fish, 2 fish, red fish, bluefish. This is the bluefish. So if you look at the diet of mako sharks, which we've done, you find that about 90% of their diet is bluefish. They're swimming around. They can eat whatever they want to, but they don't want to eat very much. They just want to eat bluefish. Bluefish are abundant, but they're also very oily, which is why some people don't like to eat them, and they smoke them or do something. A lot of them people use bluefish for bait, but it's an oily fish, lipid rich, a lot of energy. So these mako sharks, what they're doing is chasing after a fish that gives them the maximum energy return for their energy investment in swimming. They're seeking out lipid-rich fish. They also eat tuna, and they eat billfish. They eat other things that are lipid-rich. If you look at the diet of a blue shark, however, this will put this in perspective. Look at these blue sharks. They eat almost anything. They eat squid, they eat fish off the bottom, they eat fish off the top. Here's the diet of a blue shark. They're eating some elasmobranchs, not that much. They're eating crustaceans, they're eating cephalopods like squid, they're eating a bunch of different fish. Whatever fish they come along, they can't discriminate and wait for a bluefish. First of all, they might not be able to catch that bluefish because they're not the super predators. And secondly, they're passing up different prey if they're swimming along and, oh, there's a squid, I'm not going to eat that because I'm waiting for a bluefish. They don't have the luxury of doing that because they are not super predators, and they don't have all those morphological, physiological, biochemical, and powers of the circulatory system, the respiratory system, and their enzymes and muscles. So if you had a GoPro camera, this is a common thing these days. So let's watch this. Here's a shark that's swimming up behind a bait that's being towed behind a boat. This boat's probably going about 10 miles an hour, maybe. Biological torpedo. Cheetah of the shark world is what that video said.
So if you were watching that video and you didn't know anything about sharks in terms of recognizing one versus the other, there's no mistaking that as a mako shark. That boat's going fast. That shark's up there kind of like a hummingbird darting back and forth. It has to slow down in some respects because it's so fast. That is a mako shark. Whereas a blue shark's going to be cruising by. The boat's going to go right past the blue shark. There's no way it's going to be able to even keep up. So it's an interesting, very interesting topic, I think, in terms of these high performance fishes.